Hi, Allie. I'm sorry to hear there's sickness at your house, so I will tape this lesson, and we are going to be studying the conic sections. If you would label page 143 in your comp book, conic sections, that's where we're going to start. And it turns out if you take a cone that is situated on top of a cone, and I'll show you what I mean in a minute, and you slice it with a plane, these four conic sections pop out at the intersection. So let me show you that. Hopefully, I might have to turn the light off for a second. There's a little handout that you're going to get, and it looks like this. All right, do you see how we have a cone on top of a cone? And when we slice them with a plane, the very first one creates a circle. If you're looking straight down through those cones, you'll see they intersect at a circle. The second one is called an ellipse, the third a parabola, and the fourth is a hyperbola. So if you would write those four names down, we will match them to this handout when you come in. All right. I'm not going to do the degenerated ones. That was just sort of, you have to reline that. All right, and now, Allie, we are entering these definitions on page 143 as well. And do they show up? Mm-hmm. Okay, these two definitions, and we are defining our conic sections by what's called a locus definition. And locus just means location. So we're looking at the location of the points when we use these definitions. So let's see if we can figure out, the first one is a common object or common figure that we've already studied, and I'd like for you to look at it with the locus definition to see if you can even recognize it. And here it is. I want you to think of the set of all points that are equidistant, that means the same distance from one point. It says a point is a what? So, any ideas what goes in there? So we've got 1 point. That's this one that we're talking about. And I'm thinking of all the points, the set of all points that are the same distance.
Circle.
Very good.
Yeah.
All right, so say my distance was 2. So could you see that all the points that are 2 away from that one form a perfect circle? I hope so. So that is what goes in the blank right here, a circle. All right. So we started off calmly. Now we're going to kick it up into the choppy waters here. And we have the set of all points in a plane equidistant from a point in a line. So I'll give you a clue. It's one of the four conic sections that we just talked about. But does that make any sense yet? It probably doesn't until I kind of sketch it. Is that right?
Are the point and the line, they're not in the same place, right?
Right. So here's the point, and here's the line.
Is it a parabola?
It is. Very good. How'd you know that? That is awesome. And I'm going to show you why she's right. So a parabola is the same distance from this point and this line. Let me put in some candidates here. So here's the point, here's the line. So here's 1 point. I'll put little X's. That is the same distance from each. So that one's easy to visualize. It gets a little trickier. Is that us?
Is that, I don't know, is it?
10:40.
Yeah, that's not us.
20 minutes, yeah. Good, that's exactly right. So here we have the distance between a point and a line are equidistant right here in the middle. Well, what if I go out to the side? Say I pick a point that's like right there. Do you see that the distance from this point to this line is also the same? My drawing's a little off, I suppose. So imagine that we have a point where those are equal. And then maybe there's a point about right here where the distance from the point to the line are equal, and so forth over here. And that is where we get our parabola. All right. So make a little sketch of that in your under that definition, where you have a point and a line, and indicate somehow that each of those points is the same distance away from the point as it is from the line. Alright, so being in parabola land today, we are going to look at it from a little different perspective than we have previously. Check back. Is it somewhere like around page 63 where we did what we call the quadratic function?
Yeah, that was 63.
Page 63. We already addressed this from one angle, and it looks something like this. And if we had the parabola in, we were taught if it looked like this, then the vertex was, do you recall what the vertex was?
H minus K.
HK.
Oh, just
Hector
HK.
was the liar and Kyle was the truth teller. So Hector and Kyle came out to play, and remember it was always the opposite sign for the H, and the K did not change. Then we had something called the axis of symmetry, and that was also hidden in here, and it was always a vertical line. We're going to go horizontal with our parabolas today as well, and it was always x equals h. So that's what we've seen in the past from the parabola. So we're just going to look at parabolas from another perspective using the locus definition. Now I practiced over the weekend actually deriving this formula, but it takes about half an hour, so I don't think that's a good use of our time. So I'm going to give you a new equation for the parabola using this definition. So I could have went right from this definition with this long derivation. And I think what I'll do is I might just write it up for you and have you tape it in your books and just look over it so that you're not totally unaware of it, but not spending our whole day on it. So when it all boils down, here are the equations for the parabola from the locus definition. Standard form again. Standard form. Looks like this. This one I'm going to list first is a vertical one where the opening is up or down. And the vertical one looks like this. X minus h, quantity squared, there's Hector. And it equals 4p y minus k. There's Kyle. So the thing is, neither Hector or Kyle, or I guess you could say both Hector and Kyle are liars now, because the vertex is now the opposite of both of those. H and K is the vertex. And I've introduced a new letter in this mess. Do you see it? Which one is new?
P. No, Y.
Pardon?
Well, P and Y?
Pardon? We had Y before.
Oh, just P.
Pardon?
P.
Right, P. So you need to know what this P stands for. So we've got the H and the K. We're familiar with that. But the P is a new distance. It's the distance between the vertex, which is that HK spot, and the line. Remember that line we were talking about in our definition, this line, the point and a line? Notice it's not even touching that line, but that line is involved in our definition. The distance between the vertex and that line, I'm going to go back here. Do you still have that sketch in front of you?
Mm-hmm.
This one?
Mm-hmm.
Something like that. I want you to name that line, go back, and name it the directrix. And name the point the focus. So the distance, now the focus is not named here, but it is will be involved in our drawings. Distance between the vertex and the directrix is what P is. Does that show up? It doesn't look like it shows up. Lots of bells. The distance between the vertex and the directrix is what our P stands for. And we're going to put this all together so it'll make sense by an example in a minute. So write that on still, if you can, on page 143.
I'm cutting it now. I cut it this morning, but I don't know why it. I don't know.
All right, and so this one was the vertical. So I'm just going to give you the tools and then we'll pull them out and use them. And the horizontal, we didn't even cover horizontal parabolas and when we were way back on page 63. The horizontal ones, here's the equation, is a little bit different but similar. We're going to have y minus h squared equals 4p times x minus k. So that's for the horizontal one. So get that down and we'll have it all come together and make sense. I'll show you 2 problems and you'll be set to do yours. All right.
Should we?
It's a time. Yeah, why don't we close it down? We're going to start part 2 because we didn't time it.
Okay.